Hello, everybody. This is Shmuley from RSIP Vision. Thank you for joining us for this webinar. Let's wait just a few more minutes. I see that people are joining the webinar, so let's give them 3 more minutes just to join and get ready, and then we'll move forward with the webinar. Thank you. Hi again, everybody. This is Shmulik Shapiro from RSIP Vision. Thank you for taking the time and joining us on this webinar. I'll give more participants just 1 more minute to join us, and then we'll start the actual webinar. What we'll be starting with is a short introduction of RSIP Vision, what we do and how is it related to income monitoring and into the automotive industry. And then we'll move forward into the second stage of the webinar, starting actually talking about the applications, challenges, and all sorts of R&D related issues that we would like to present to you today. Joining us on the webinar is Daniel. I'll be introducing him in a second, and we'll take it from there. Okay, that's it. So people are in. We have a nice amount of people. Let's start the webinar. So for the last time, thank you for joining us. This is Shmulik Shapiro talking. I'm the Executive Vice President of Global Business Development at RSIP Vision. And joining me for the second and more important part of this webinar will be Daniel Tomer. He is the automotive team leader in the company, responsible for many of our automotive industry related developments. So as I said, I'm just starting to with a few slides to present RSIP Vision and what we do and how are we related to this field, and then we'll move into the more interesting subject, of course, of the in-car or in-cabinet monitoring. So basically, RSIP Vision is an expert group in image analysis and deep learning that's our specific expertise, and that's what we are doing for the last a bit more than 20 years for many clients now. Basically, what we do is we develop algorithms and deep learning solutions for computer vision and vision-related projects. In some cases, it's going to be classic image analysis development, classic algorithms, and in different cases, it's going to be deep learning solutions. Of course, in the last few years, so we have more and more deep learning solutions because if you have the right conditions, the right data, and so on, so it will be very robust and very accurate. Eventually, we work as an outsourcing solution for your different companies and many automotive vendors as well. Some kind of extended R&D team or specialized R&D team of the company working closely with the internal team and pushing forward the roadmap and different kinds of R&D and projects that we will be presenting shortly, at least some of them. Mainly, we have a bit more than 50 engineers, and in the States we have 2 offices, one in the Boston area and one in the Bay Area in San Jose, and we have an R&D center in Tel Aviv as well in Israel. In the automotive industry, we've been working for a few years now, and we have experience in different kind of projects. So we have experience in projects looking outside of a car. So it could be, of course, cameras and perception-related projects. It could be LiDAR. Okay, for example, we've dealt a lot with artifact corrections, data cleanings, things like that for different kind of challenges. We've done projects around sensor fusions looking outside the car, but also in-cabinet applications like we're going to talk later today. And basically, we have a few clients we work with. If each one of these different development solutions, we'll be happy, of course, to have more of these. In general, we have a lot wider experience in different kind of technological verticals. So you can see here just a handful of examples for our capabilities and experience. We have a lot going on in medical devices. We have projects in smart agriculture, agritech, and different kind of, I would say, industry-related projects. But all these eventually is building up the capability and the know-how in the company that's related eventually to the automotive industry. Just for example, in the last few years, we've been dealing with LiDAR technology going into the automotive, but we've been dealing with such solutions for many years in both in the industry in medical applications as well. Perception, if we're talking about different kind of segmentation and classification projects, so we've been doing that in different kind of medical related projects like CT, MRI, even ultrasound for many years now. So all this accumulated experience and know-how was very natural for us to take it to the next stage into the automotive industry. As part of believing that we are part of the AI community in general, and we have a lot of passion to these fields, so we've been doing a few things for the community. So the biggest thing, and we're very proud of that, we are the owner of the publishing of a Computer Vision News. That's a monthly magazine dealing only with computer vision, AI, and related solutions. Very fascinating things going on over there each month with deep interviews and a lot of innovative stuff being presented over there. So that's one thing. Also, we are the official partner in many different kind of conferences. So it could be, the CBPR and the MICAI, of course, the known ones, and we have a handful of automotive conferences as well. You can see on the screen that we are an official partner to them. So that's once again part of our belief being part of this beautiful community. And this webinar as well, and different kind of meetups that we are organizing, is just part of who we are and the passion we have towards this field. And I think that's enough. I mean, you didn't come here to hear about RSIP Vision only, so maybe we'll move forward with the actual issue that we are going to talk about today, and that's the in-car monitoring or in-cabinet. There are a lot of different names around this field, and let's move forward with that. I will start with presenting the main applications in the field, and then I'll give Daniel Tomer, once again, the automotive team leader in our company, to talk about the technical challenges and different prospects of the R&D development in related issues. So I think the first thing we should talk about very shortly is who needs it and why, right? At least that was my initial feeling when I discovered this field and people started talking with me around it. So there are a lot of answers to that. I think the most basic one is safety, right? So we want to increase the safetiness. I think maybe the first subject will be the driver, and then the safetiness of the rest of the passengers in the car. And of course, that's easier to understand. So we're going to talk in a few minutes on different kind of safety-related applications, but a lot more is going on. So actually, I would say that the safety application is dealing with, let's talk about the autonomous driving. So stage 1, stage 2, maybe even stage 3, but the rest are looking forward towards stage 4 and stage 5, right, of fully automated cars. And not only that, but we actually now understand that the trends in the market are more or less divided into two different, I would say, revolutions. The first one, what's starting to happen, and we've been seeing that actually live in the last CES in Vegas, you know, automated taxis going along the strip and taking passengers. So that's the first revolution, dealing with mainly taxis and Ubers and things like that, share ride solutions. And the next stage will be the more personal cars, private cars and things like that. And there's a big difference between the two of them. So actually, we're seeing some kind of shift focusing from the driver to the passenger, right? Because if he's not driving, he's not the main factor of the safety, because we have all these systems. So who's actually inside the car? What is he doing? What does he like doing? How are we going to spend the time inside the car in a more pleasant way? So that's becoming a big issue. And some are talking about the third living space revolution, right? So we're moving from a product-centered, I would say, maybe economy or vertical, to experience-centered. We've been seeing that along during the CS as well. How can we make, you know, the time inside these vehicles, inside these taxis and so on, more efficient, more convenient, more pleasantable, things like that. So that's becoming a big issue. And that's why we're actually talking about optimizing between safety and comfort, both of them together. So it's some kind of balance, moving towards comfort, as I said, as more and more we're getting closer to the fully autonomous cars. And the last thing, of course, is regulations. So we're already seeing a lot of, I would say, talking about regulations. One of the examples that I've seen an article talking about more and more people taking Uber, you know, or Lyft or something like that when they want to get to ER instead of inviting the ambulance, just because it's cheaper, it's more, it's quicker, more efficient, and so on. And there's a lot of questions around liability. Okay, who is in charge of what's going on in that case? Is that the driver? Is that the company? And what's going to happen if we don't have a driver? And what's going to happen if somebody isn't feeling well inside that autonomous taxi? So there's a lot of talking about regulations in this area, and this is, of course, influencing, again, all these different applications. So I think who needs it, we talked about, and why, but I would say who is actually everybody. All the manufacturers, all the tier ones, everybody's talking about it, dealing with it this way or another, because there's a lot of implications for this when the market is evolving. So basically, we're talking about two main application types when we're talking about the in-car monitoring. The first one, like I said before, is driver monitoring, more safely related, and the second one is the wider view, the cabin sensor or cabin monitoring, and so on. And let's dive into the first one. If we're talking about the driver monitoring, so basically we're talking about real-time monitoring of the driver's behavior. I would add here in the state to prevent accidents. Okay, so I'll put on the screen just a few examples of the companies providing different kind of solutions here. So we're talking about gaze vector, head pose, okay, things like eye openness or yawning. Okay, we want to better understand is the driver concentrating now on the road, on driving, or is he looking aside? Is he very tired? Is his head moving, up and down and to the sides? And that's a risk factor. Some companies are offering blink rate. Okay, how many blinks per second or per minute is he actually doing right now? And that's another factor that may tell us that he's tired, right? And he's struggling, to keep himself awake and concentrated. What can be done with these applications? That's another issue, right? So if you know, or if the algorithm feels that he is tired, what are you actually going to do with that? Different vendors are, I would say, attacking that from different directions. Some of them will have alerting systems using voice, some using light. I've seen companies even develop them some kind of a small device that will be located next to the leg or next to the shoulder, and giving some kind of movement indication to the driver to wake up. So there's a lot going on around that, but we're not talking about that. We're only talking right now about the actual detection and the monitoring in regards, once again, to preventing the accidents and make sure that the driver is concentrated on the actual driving, because as we all know, unfortunately, that's a great deal of car accidents is because of this thing. The second kind of applications we're going to talk about is the cabin sensing or cabin monitoring. Like I said, the wider view. And once again, we're talking here about real-time monitoring, but this time not the driver, but the cabin interior. Okay, and we have a variety of both safety and entertainment reasons. Some of them that we can see here is, for example, seat occupancy, and that's maybe a bit more straightforward. Okay, we want to understand who is sitting where and how many people are inside the car. And that's related to mainly to safety, but also to different kinds of engagement that the vendors want to have with the passengers inside the car. We're talking about, for example, age and gender. Okay, so if you want to give a better experience, you want to understand who are actually the passengers in the car. Maybe you'll change the music, maybe you'll change the lighting inside, things like that. So there's a lot of things going on around that. Emergency situations, of course, I gave you an example just a few minutes before regarding people taking more and more Ubers and Lyfts and things like that to hospitals instead of ambulances, but also what happens if somebody gets a heart attack inside the taxi, okay? Who is going to alert? Now you have a driver that can take him to the hospital, but what's going to happen if there's nobody inside, right? So that's a thing that needs to be taken into considerations. Maybe I'll jump forward. You can see violence. Okay, so what if it's once again a taxi and somebody's fighting inside? What's going to happen? Do you want to detect it? Do you want to alert it? Would you like to stop at the side? You need to understand what's going on so you can act accordingly. Things like child seats. Okay, so that's a very important application, just to understand that there's a child inside the car and to make sure, nobody, God forbid, forgets, the child after they get out of the car. So there's a lot of safety issues here. And the last thing I think maybe is very interesting as well, the surface condition. That's starting to be a big thing now. And I think we can all actually relate to that, because how can these autonomous vehicles, and mainly once again autonomy taxis, how can you make sure you're going to enter a clean taxi? Okay, you don't want to have a bad experience, right, and sit inside a very I would say dirty taxi or something like that. So these companies need to have a way to understand that everything's inside okay, nothing is broken, okay, nothing is extremely dirty or something like that. And that's a main application going on today. So we've seen a variety of different kind of applications. Some of them very relevant already right now, improving, different kind of safety um, um, objectives, and the other more related to the experience and to entertainment and things like that. There's a lot going on in this field right now. So you can see now on the screen just a bit more than a handful of companies working very hard, to get these applications into the market. All of them are working with different kind of manufacturers and tier ones to provide these technologies. Some of them are very advanced, already installed in, I would say, test cars and so on, and have agreements with different kind of vendors. Most of them, I think, raised a lot of funding until now. Like I said, it's like a blooming field right now, and there's a lot going on. And I think we're going to see a lot more happening in the next couple of years, because that's actually the time frame we're going to see more and more autonomous taxis getting into the market and actually starting the real revolution, because we're going to get used to that experience and seeing them around us all day long. So that was just a quick overview of main applications today when we're talking about in-cabinet or in-car sensing. And I'm going to pass the lead now to Daniel Tomer once again. He's the autonomous team leader in our company, leading a lot of the developments for different kind of vendors in this field. Daniel, are you with us?
Yes. Hi, Shmulik. Thank you for the great introduction. Okay, so let's begin with the more technical part. And as Shmulik already presented, our main objective is monitoring the in-car passenger behavior. For that, we first need to understand or decide what's the arrangement of sensors inside the car that we want to use to do this task. And there's a variety of sensors that we can use. For this task, we have regular RGB cameras. We can use depth cameras for for a depth look on what's going on. We can use motion sensors or weight sensors. We at RSIP are more interested, or let's say our expertise is more in interpreting the output of the sensors. Usually what happens is we get a customer with, say, an existing arrangement of sensors and their outputs, and we help them understand what they're seeing, or to get as much information as possible from all these sensors. Of course, because also a lot of the time we help tweak the sensors, or maybe choose another one that can help us with the task. But most of what we do is interpreting the output of the sensors using different algorithms. In this presentation, I'm going to focus on one specific test case of a sensor arrangement, a very simple one, which we've encountered before in our projects. It's one in which the only sensor input is a dashboard RGB camera. It may seem like a very simple case, but I think we'll see that there's a lot of information to extract from such a simple arrangement of sensors, and a lot to learn from it, from all kinds of arrangement afterwards that you can add on top of this simple case. So we can go maybe to the next slide. Okay, so first of all, after we have our sensor arrangement, we need to choose the right algorithm for the task at hand, which is, as we said, to extract as much relevant information as possible from a video stream, our RGB camera video stream. So we have two main options to go with when talking about computer vision in general. We can go with the classical image processing algorithms. These are a group of algorithms which are mainly based on human logic. A developer or algorithm developer needs to sit down and say explicitly to the computer or to the program, you need to do step 1, step 2, step 3 in order to achieve what we're going for. Sorry. These algorithms, some of which are like optical flow that gives us motion in the video, ransack, hop transform. The problem is with these algorithms is that when they're facing problems with high variance, when the algorithm needs to face large diversity in cases, these algorithms are not very robust. For example, for today, up until today, we're not really able to write a logical step-by-step guide that can accurately say if an image is containing a dog. The diversity of cases is just simply too large for a step-by-step solution. But this is not to say that we need to neglect these algorithms, not at all. They're still very much in the game. They can certainly help us with pre-processing and post-processing, adding extra features to what we'll talk about next to our machine learning algorithms. But they're for computer vision tasks. They won't be our main algorithm. They'll be more of a helpful algorithms that help us add more information. So instead, as we said, we will use a machine learning algorithm, and more specifically a neural network, which are a subclass of machine learning. So let's talk a bit about machine learning. They also divide into two main categories. There are the classical machine learning algorithms, such as linear regression or logistic regression, support vector machines, random forests. All of these work best when you give them specific features, typically not too many features, because they don't scale well with many features computational wise. And again, a human developer needs to decide most of the times what are the most relevant features for the task at hand. He needs to carefully pick them and input them into the classical machine learning algorithm in hopes that these are the actual features that the algorithm needs to make an accurate prediction. And on the other hand, we have the neural networks, which take mostly raw input. In computer vision especially, they take a raw video frame or whatever and extract the features, and by themselves they extract the features that are most suitable for the task at hand. And this has proven many times to be the best and most practical approach when dealing with raw camera inputs. Also, neural networks we can say divide into three main categories. We have the unsupervised learning models, which find patterns in unlabeled data. This is not something we usually use as our main algorithm. Also, we can use it in post-processing or stuff like that to compress image or stuff like that, but not the main algorithm again. We have reinforcement learning, which is algorithms which find the most suitable action in a given situation. This is more relevant when your task is something that you can frame as a game, as something that an agent playing a game needing to decide what to do next. Again, less relevant for our problem of in-car passenger monitoring. And last, we have the supervised learning algorithm that it's mainly training a model to perform a task using labeled examples. We show the model the input, we show him the accurate output. He learns and generalizes for inputs he hasn't seen yet. This is by far the most widely used method for practical applications, especially in computer vision and specifically in in-car monitoring. So in the next slide, we can see that, okay, if we chose to use a supervised learning algorithm, the first step in this is gathering a data collection strategy. We have to have good data. We have to have accurate data. This is a very crucial step because the model is as good as the data used to train it. You can never train a model if your data is not a quality database. I'll try to point out some tips and considerations that we've accumulated in RSIP along the years. that can help when planning this specific phase. So you should know from the start what kind of model you're planning on training. You want to know what's going to be your input. You want to know what you expect to be the output, and you want to collect your data accordingly. For example, in our test case, the one with the one RGB camera live stream from a car, there is at least 2 options that need to be taken into consideration. We can use maybe a recurrent model, recurrent neural network, which is a model that utilizes the temporal dimension. It has temporal awareness. It does this by accepting its input is a sequence of frames. And when trying to predict what's going on in the frame, one of the input is the output of the last frame. The prediction of the last frame is an input to the next frame. And in this way, the model is able to be aware of the temporal dimension of what's going on temporally. If we want to train this kind of network to detect passenger in a cabin, let's say, we will have to collect the data which has examples of all the options that can happen time-wise, all the possible movements. This, of course, is on top of the diversity we need to create in our database regarding the passengers themselves, their position, their pose, their look, all of these stuff. We need to have a lot of diversity in our database if we want our model to generalize well. We can't expect the model to understand situations that he had never seen before in the training data. I mean, you don't have to show him the exact case because that would mean that he didn't learn anything, but you have to show him similar cases that he can learn later to generalize over. So this means that it's a fairly large amount of data you need to train this recurrent network. On the other hand, you can train a per frame model, which only predicts according to a single frame. This will take away the temporal awareness that the recurrent model had. But we will need less data to train it because we won't need to give it all the diversity time-wise, only diversity in the passengers themselves. This will also directly affect the amount of time we will need to spend on labeling the data. If we need less data, we need less time to label it, of course. And another advantage of a pair frame model is the shorter training period relative to recurrent models. The recurrent models typically take, this really depends on how large your database is, but it's about an order of degree higher than what it takes to train a pair frame model. Both directions are valid, of course, and mostly depend. To choose one of these mostly depend on the practical considerations of time and effort available for the project. We don't have time to cover both options, so in this presentation we will focus again on a per frame approach. We will see that maybe even for a per frame model, we can utilize the time dimension in a different way, maybe not in a machine learning way, but in a more classical way. And then, and by this, we will get the temporal awareness without having to get data to train it directly. Okay, so now regarding I'm not finished with that. Let's go back. Yeah, okay. Another thing to consider when annotating, is the annotation process itself. It's very tempting. We saw it a lot of times to use companies that only do annotations for labeling your data. But we found through experience with a variety of projects that using this offhand approach often leads to a low quality database with many outliers and inconsistencies, which can confuse your model later on. We found that the best way to go about this is to combine an in-house annotation team with this outsourcing, which is usually cheaper and they more large scale, a lot of workers working on it in combination, but you also need an in-house annotation team, and I'll explain why. The in-house annotation team will usually be in charge of the more complicated tasks. They can easily interact with the development team, which gives us it helps us with ambiguous problems, with ambiguous cases. If the annotators are not sure what to do with a specific case, they can go directly to the developer, ask him what he thinks about it. The developer usually has a lot of information about what he's planning to train, what's the objective of the labeling, and he can answer him directly and avoid mislabeling and outliers. The outsourcing can be used for less complicated and more straightforward tasks, things that don't need that are not too much ambiguous. This is exactly how we work at RSIP. We hold an experienced, highly skillful in-house annotation teams, which gives us high-quality annotations we can count on. And we use outsourcing, which is supervised by the in-house team for the less complicated, large-scale annotation projects. Okay, so another challenge that we have to encounter, this is not directly related to in-car monitoring, is training a model while the database is still being collected and updated regularly. A lot of the time, the customer starts out with a project, he starts accumulating more and more data, and he wants and you want already a model working before you finish collecting all your data. In this case, we first and foremost need to build and work with a version control system. This is the most crucial part. This is on top of your Git control version. Git is not enough in this case, and I'll explain why. Throughout the development process, we train many models, and each of these models needs to be reproducible at any point in time. And for this, we need to know exactly what data was used to train it. We need to know what data was it tested on, mainly for comparison reasons with neural models. We will need to know what's the architecture, what's the hyperparameters, what was the weight initialization process, and so on. And this is crucial if you want to be able to understand and have confidence in any upgrade in performance. I mean, if you have now a model that you think is performing better, but you can't really compare it to earlier models, then you won't be confident that you gained any progress. So this is a real crucial point when you have data that is accumulating in time. Another issue with the changing database is how to incorporate new data into the training process. So you have already a working model, and now you have extra data, and you want to improve your model with the new data that you added to the database. Constantly retraining the model from scratch is very time consuming and doesn't necessarily provide the best results. So we'll go through this a bit quickly. So we have a couple of ways to do this. We can use transfer learning when we start from an early model, and then start training from not from scratch, but from a model that is already working. We need less epochs and less training time. We can use weight freezing when we only train a couple of layers in the model, not the whole entire model. This also gives us a very fast training time. And we can use high exposure to new data in order to make if the new data is completely different from what we already saw, then we will use high exposure to the data. We'll use a different loss function that gives higher higher exposure to the new data added. Another thing with the diversity of the data is another issue when the data keeps growing is that a lot of the time the diversity of the data also keeps growing. What I mean for this is like if we have the in-car monitoring problem, then we start off by only filming adults in the car, so our model is working well on the adult human passengers. But then we suddenly want to add kids, so our model will also be able to recognize kids. So this is a new diversity in the data that we need to carefully account for. We do this. We need to reevaluate and update the test set, so we will account for the new diversity. and we need to have constant communication between the data collection and the development team in order to know exactly how much of this new data do we need, and maybe to avoid adding too many complications too fast. We need to take it one step at a time to not confuse the model too fast and accumulate more and more features in a controlled manner. Okay, so we can go to the next slide. Okay, so let's dive into the actual per frame models we can use in our problems of in-car passenger monitoring. We'll elaborate on a couple of these in the next slide. So we have occupancy classification using a regular classification models. For each frame, we will output the per seat probability of the occupancy. Face detection that will output the bounding boxes of detected faces. Pose detection that will output key points of all the detected passengers. We can use head pose models for driver monitoring, outputting the pitch, yaw, and roll of the driver's head. This usually comes also with a gaze vector that outputs a vector indicating the driver's direction of gaze, helping us decide if we need to start an alert or anything like that, knowing where the driver is looking at. Okay, so let's dive in, elaborate on a couple of these. So we have occupancy classification. We want to know exactly for each of these models what are the advantages and what are the shortcomings of each of these models. The final solution will usually combine all or some of these models. So we need to know exactly what they're good at, what they're less good at, to know how to combine them at the end. So let's take, for example, this occupancy classification. Its main advantage is that it can be made very fast and compact. It's not a very hard task, so it doesn't take a very large network to do. Annotations for this kind of model are very fast because there's not a lot of information here. This is also one of the shortcomings of this kind of model. And one of these advantages is that it produces localized outputs. This looks very straightforward for this specific model because that's what we ask him for in advance. But we will see that in later models, this is not very straightforward to localize the outputs. Here we know that each output is associated with a certain seat. Later, if we see like a phase detector, we don't know exactly what seat it's associated with, and that's a disadvantage. For this model, it's an advantage. We already know what probability is associated with each seat. What's the disadvantages? So it gives us limited information, which is only good for a limited amount of applications. You get only information about the occupancy of the seat and nothing else. And it's very sensitive to occlusions, but this is something that actually is true for all pair frame models in this specific arrangement of sensors, because as you can see, the back seat is almost half occluded. So anything that's hiding behind these chairs, these pair frame models won't be able to see it, and we need to think of other ways to account for people being behind chairs. Okay, so we can go to. Yes.
Yeah, I'll just add, Daniel, that we are running a bit late, so probably we're going to take 5 more minutes of your time. Let's try to push forward a bit quickly so the participants can see, the rest of the applications. I'm sure they're waiting to see that.
We'll go through this very quickly. We have phase detectors. You can see on the right the open source phase detector, which is works pretty well when you have a good camera angle and you have a nice high-res camera. Open source, we a lot of the times we have sensors that are less high resolutions, do a distortion of some sort, and then these kind of open source solutions don't work as well. And then we have to make a customized model to perform better on these cases. We can't show them here because it's non-disclosure with our customers, we can show actually what we provided for them. Okay, so let's move on. There's advantages and disadvantages, but we can see, let's see what else we can do with our one camera. We can also do pose estimation. Again, we can see the open source solution on the right. The problem, it's a good solution, also not working as well when you don't have such a high resolution video. And also it's a very computational, inefficient solution. So it actually tries to solve a very hard problem that in-car monitoring doesn't exist. In-car monitoring is a lot more constrained than the models that are used for unconstrained environments, multiple, that you don't know how many poses you're going to have in the video, you don't have any maximum number. So the solution used to solve this are very expensive. Actually, in the car, you can maybe use simpler models to do the same or even better jobs if they train specifically for these tasks. This last problem with this is the annotation is very time consuming. There's a lot of information to do, and it's prone for errors because of the difficulty. You can switch left, right, you can switch the eyes, stuff like that. Okay, so these are the models we can use, the AI models, but how can we combine them all together into one? How can we still utilize the temporal, even if we didn't train any models that utilizes this dimension directly? So we can maybe use a common filter. I have here an example of what a common filter is. I'll go through it shortly. So it helps us combine multiple sensors, and it utilizes the expected behavior of the system we are monitoring. For example, we can use it to track a drone's position. If we have periodic measurements of the drone's position and velocity with GPS, we can estimate where, using basic Newtonian physics, we can estimate where the drone is going to be later on. And then combine this prediction, this expected behavior, with the actual new measurement coming in from the GPS. Together, you'll get a better than better estimation when combining all your data together. This is what a Comm Filter basically does. So in the next slide, how do we actually use this? How can we utilize this Comm Filter in our in-car monitoring? So let's take a specific example of occupancy classification. We want to know who is sitting where. So let's say we have both predictions from the pose estimation model that tells us there's a person here and here, and the occupancy detection, the one that only outputs probabilities. So we can combine both of these using this Comm Filter. And we can also add inputs such as door states, if the doors are open or closed, and we can use a motion detector. All of these are inputs to the Comm Filter. And the expected behavior, instead of Newtonian physics used in the drone example, here Newtonian physics won't help us because people are a lot less predictable. But we can expect certain behaviors from passengers, specifically passengers in cars, as you can see in the chart in the right. We can expect people to move in the back seat or get in or get out of the car, assuming that the doors are open. But we don't expect a person in the back to move to the front seat. It can happen, but it's less likely. So we can use this expected behavior in our Comm Filter to get a more accurate predictions and more stable in time predictions of what's going on inside the car. If we also add like door status, we can even prohibit certain changes. We can say if we saw a person in the back seat and the door is closed, it's probably, even if I'm not seeing him now, he's probably still there. Okay, so to conclude, there's a lot of things we can be achieved when using AI algorithms for in-car monitoring purposes. Most of the problems require a solution which combines several AI models and classical image processing techniques. And the best solution are always the ones that are customized for a specific problem. We at RSIP are more than happy to help you with developing your solution.
Great, thank you very much, Daniel. It was very interesting, and I hope everybody else feels the same and found it very interesting webinar and lecture. Thank you very much. Let's take 1 or 2 more minutes. Just if anybody has any questions, please use the system to send us a question, and we'll be more than happy to answer that. And for the rest of you, thank you very much for joining. We'll be happy to see you in the future. And of course, if you have any relevant projects that you would like to consult with us, please feel free to contact us using the website or any other connections to our company. Let's give him another second and see questions that are raising here inside the system. Okay, so one question I can see here is asking for an example for a more complicated annotation that we estimate that should be done, in-house, in opposed to using outsourcing company. Daniel?
Yeah, so here at RSIP, we also a very simple example for this is the medical projects we do, which actually need people with specific expertise in medical imaging and stuff like that. You can't send it out. You need an experienced team. But even also in car monitoring, which all seem pretty straightforward annotations, we found that, let's say, pose annotations can be very difficult for an outsourcing team to do. There's a lot of ambiguous cases, people that you can see only half of their arm, or you can estimate where the knees are, but you don't know for sure if they're there. And a lot of times when you send it to an outsourcing company, you get all sorts of annotations. Each annotator thinks of a different way to interpret it. So for that, we would actually prefer using an in-house team that can ask the developer at every stage what he thinks is the best way to annotate this in this case.
Okay. One more question we have here is related to the timeline. If you can give us some kind of estimation, how much time does it take to develop one of these application or example of them?
Yeah, so this really depends on the scale of the project, of course, but usually, let's say typically we take the first 3 months or so to develop a prototype, a proof of concept to what we're trying to do, a model that can actually give predictions, maybe not the best one, maybe just on a subset of the training examples or something like that. And then there's an ongoing development process, usually driven by failure analysis. We see what the model is good at, what it's less good at, and there's an ongoing process of adding more features, adding more capabilities to the model. This can take as long as much as you want the model to have more and more capabilities. Actually, you can add more models later. It's an ongoing process.
Okay, so we are running late. I'll take one more question over here, and the question is, how would you handle people leaning forwards, back, or to the side, etc., for occupancy classification?
Yeah, so there's a problem with that because of the per frame that I use. So one solution is, of course, the recurrent models that can see what happened in earlier frames and use this information to infer what's going on right now. Another solution is what we tried to show. We did it a little bit quickly, so maybe it wasn't very clear, but the Comm Filter actually can help us a lot with this if we give him more information about what the possible movements are in the car, or what are the most probable movements, not the possible, because everything is possible, but only a few things are probable. So this can help us a lot with determining if a person leaning behind the seat is still there or not, and stuff like that. So it helps us a lot with this kind of problems.
Great. Okay, so that's it. We ran out of time. Thank you, everybody, for joining us today for this webinar. Once again, we hope you had a very interesting webinar and a great time. We are looking forward to seeing you again in one of our next webinars or meetups in the Valley. Daniel, thank you very much for this fascinating lecture and of examples you've shown us all. And please feel free to contact us once again with any project you may have inside your company, or any question that you have related to one of these issues. We'll be more than happy to answer them, address them, and hopefully maybe work together in the future. So everybody, thank you again. Have a great day, and bye-bye for now.